Hi again. In this lecture, we start the algorithm efficiency topics. So in this one, we will make a gentle introduction to what is algorithm efficiency. And in the upcoming ones, we will shed more light to the asymptotic notation and how we can use asymptotic notation to make a thorough analysis of algorithms. Okay, so let's start with the basic question. How can we measure the performance of an algorithm? So let me tell you about the story a little bit. In the late 50s and maybe early 60s, after the World War II, there appeared programmable computers available in the market. And once we have those programmable computers, surely there appeared the programming languages, Fortran, Algol, and later Pascal. Okay, and people started devising algorithms for some problems, and those algorithms are to be run on those computers. And very soon there appeared a necessity. Okay, so once we have the algorithms for a problem, how can we measure their performance? And for that reason, the first metric for the performance of an algorithm is surely its correctness. Without the correctness, it is not an algorithm. And as we discussed in our previous videos, so what is correctness? So we say that this algorithm runs on all legitimate inputs and provide us the correct output. So that's the correctness, and that should be something provable. Okay. But once we have a correct algorithm, how we will measure its efficiency? To measure the efficiency in 65, so the two researchers, Manis and Stern, they just proposed to use the time and space complexity, which was very intuitive. So whenever I have an algorithm, I want it to be fast, providing me the output as soon as possible, as quick as possible. And I want it to use minimal resources. With the minimal resources, generally we mean minimum memory. These days, energy is also in the play, but we do not have a mathematical model yet to measure the energy efficiency. So we still go on with the early definition of the efficiency, which is based on time and space complexity. And we will be mostly talking on time and space complexity in this course. Okay, but that is the main part. However, there is also a third dimension that I would like to tell you a little bit about. In the late 60s, so Donald Knuth started writing the seminal book, right? So The Art of Computer Programming. And in this book, the name is also very interesting because it is the art of computer programming, which says actually there is an artistic dimension in the actual programming practice. Okay, and as a third dimension, I would like to include the elegance of an algorithm as a performance metric. Again, it is not something mathematically we can measure, but I will try to sketch what is elegant throughout this course. But to be simple, what is elegance in the dictionary? Elegance is defined as the beauty that shows unusual effectiveness and simplicity. In programming, in algorithm design, elegance means that is something you can easily communicate with others. And since you can easily communicate with others, it is also very simple to code. But we will be focusing on this dimension later. Today, we will be talking about time and space complexity. Okay, so once you have different possibilities to solve a problem, different algorithms, and you would like to learn about their performance, you would like to learn about their efficiency, then it is very intuitive to implement an algorithm, run it on a machine with a specific input you provide. That is very easy. We call this the experimental approach, because at the end, you will have the precise metrics, the precise answer to how long will it take to run on a computer and how much space it will occupy. So such an experimental approach will surely provide us a very precise measurement. However, notice that it will be specific. Specific to what? Specific to the implementation. What is the implementation? Which language is used? And it will be specific on the machine. So what is this machine? What are the specifications? Which CPU? What type of memory you are using? And it's also specific to the input you provided. Maybe I provide an input that's cherry-picked and it will be favoring my algorithm. I don't know the general result, okay? So that is why for the experimental measurement of the efficiency, we can say that it's very precise, but it is specific. On the other hand, if you make a theoretical analysis, which means I don't want to be specific to the implementation. I don't want to be specific to the computer. I don't want to be specific to the input. I want a general answer for the efficiency of my algorithm, okay? Then we are chasing an accurate analysis, accurate results. So at that point, let's turn our attention to the difference between the accuracy and precision. Okay, so what is accurate? What is precise? Precise means you make a lot of measurements, and those measurements are very close to each other. For instance, you run your program on a machine and you repeat this experiment a lot of times. You expect to have the measurements close to each other. So that means that's a precise measurement. On the other hand, accuracy is how close the measurements to the truth. Okay, so I may have a lot of measurements, they might be close to each other, but that doesn't prove me, that doesn't guarantee me that the result is accurate. On this graph, okay, you see here some measurements. They are very precise, but they are not accurate. They are far away from the center. Here, on the other hand, I have some measurements. Those measurements are not very close. However, they are very close to being to the truth. Okay, so I can say that. So that's a accurate but not precise implementation. Surely, what we want is everything to be accurate and precise. Okay, which most of the time we do not have this luxury. Okay, and this not accurate and not precise is not something on the table. So roughly, if you are making a theoretical analysis of your algorithm, you are having an accurate answer, but this will not be very precise. If you are making an experimental analysis of your algorithm, that will be very precise, but we don't know whether it is accurate or not. Okay, so with the theoretical analysis, actually we do not need an implementation, we do not need a machine, okay, and we assume a general input. Okay, so we say that, okay, given the pseudocode of an algorithm, what I will do is I will measure how many times the instructions will be executed, and I will measure how much extra space will I need during this calculation? And I would like to do it on all possible inputs. So that is why it will be a very general answer. Okay, now let's discuss the experimental analysis a bit more in detail. Okay, with the experimental analysis, I'm implementing the algorithm and running it on some outputs. What are the specifications of such an experimental analysis? So here is the ones that, the major ones, there might be more of them. So for instance, the programming language. You implement an algorithm in Java, you implement an algorithm in Python, you execute them, you run them, and then you will have different timings, right? Because of the programming language specifications. It also depends on the programmer. Maybe the programmer is an experienced programmer using better instructions, more sophisticated instructions, writing the program more efficiently. So that is why even the same algorithm will not have the same efficiency between different programmers' implementations. What is the compiler? Okay, so you fix the programming language, you fix the programmer, but even the compiler makes a difference. So LVM compiler, Intel's compiler, GNU compiler, whatever. Okay, so there are many options, and choosing a different compiler will have an effect on the running time. Also, the machine. So the computers have different processors, right? So it might be an Intel processor, it can be an AMD processor, an Apple processor, I don't know. So there might be many difference. And also the architectures may be different. So what kind of memory you are using, how it is connected, and the architecture, IO channels, everything. So that is why an experimental analysis of an algorithm is highly specific to many specifications, but it will provide us very accurate, very precise results. Okay, with the precise, I mean it will say 3.2 seconds by using, I don't know, 121 megabytes of memory, something like that, very accurate. Okay. However, such an experimental approach will not be able to answer some further questions. We will see that actually our main curiosity in the algorithm analysis is how long will it take on larger input sizes? For instance, you have an algorithm that runs on a 100 integer long array, and let's say that takes time t1, and you are curious what it will be if I run it on 1000 integers. Okay, so you have the measurements for this one. Okay, this measurement, can it tell you anything about this one? Actually, no, because it is specific to that size and it doesn't tell anything about the larger one. So that is why with the experimental analysis, we cannot answer this question. Yet another question is, okay, I'm running this algorithm on this input, but how about this input? Is it a best case scenario? Is it an average case scenario? Is it a worst case scenario? We will see what best, average, and worst case scenarios are very soon. But what I would like to say is, so depending on the input specifications, the running time, and the required memory, so they may change very significantly. A third question is this an optimal solution? This is a bit more sophisticated. That requires beyond algorithm analysis, maybe, that we will be studying in this course. But that is something we should know. Is it optimal means, would it be possible to come up with a better algorithm to answer this question? If no, which means that this algorithm is not optimal, and then the research will continue to find a better one, right? But if this is optimal, then theoretically, this is the minimum number, this is the best way of achieving this calculation, computation, and we will more focus on engineering, programming of this algorithm. Okay, so that is about the experimental analysis. So when we come to the theoretical analysis, the theoretical analysis answers our main curiosity. We have an algorithm, and we would like to know what will happen when we execute this algorithm on larger and larger input sizes, even assuming the input size comes close to the infinity. How can you answer this? With the theoretical analysis, which is the backbone of this algorithm's course, we will assume the abstract machine. We discussed that machine previously in our previous videos. So the word RAM model, okay, so that's a random access machine. And we will simply, that is important, just count, oh, sorry, here, right there. Okay, we would like to just count how many instructions will be executed. So this will give me the time complexity and how much additional memory will be needed, both of them on an input size of n. So this is a theoretical approach, and this count and this measurement, okay, so they will be giving us a function of the input size n. More precisely, I will say that if t is the running time of this algorithm, Tn is a mathematical function that gives me the number of instructions this algorithm will be computing, okay? And the space complexity as a function of n will tell me on an input size of n, what will be the extra space that I will need while doing this computation. So these are function of the input size. With this approach, since I have the Tn function and the Sn function, I may consider what will happen when n goes to infinity. And this will give me the answer of my main curiosity, what will happen when n gets larger and larger. The good thing with the theoretical analysis, you don't need to execute any code, and even you do not need an implementation. The only thing we need is an accurate pseudocode, which is enough to run our theoretical analysis. So let's have a very basic example. So we would like to analyze the sequential search. Okay, and on this search, we will see what best first and average case scenarios mean. Okay, sequential search, very easy. So we are given an array of size n, and we are looking for an item with k. For instance, so let's say this a is equal to something like 1, 5, 2, 100, -7, whatever, okay? And I'm looking for 100 in this array, okay? So to look for the 100, what I will do is I will pass over this array one by one, and I will check it, right? So 1 is not equal to 100. 5 is not equal to 100. 2 is not equal to 100. And on the fourth element, I will hit to 100, which is the key I am looking for. And then I will return that. Yes, I found it. I found it at position 4. Okay, so this is the algorithm we are talking about. Okay, good. Now let's try thinking about that. this is my code. I start from the initial, and while I do not hit to the end of this array, what I will do is I will check one by one whether the array item that I am currently on is equal to the key that I am looking for. If they are not equal, then I will increment the position by one and keep checking. Now, if you run this algorithm on an input of n, and if you provide that key to be something different than the elements in this array. Again, if array is equal to 1, 2, 5, 700, I don't know, -2, whatever. And if I say that, okay, I'm looking for key 200, this will be the worst case. This will be the worst case because I will need to check all of the items in the array, and at the end, I will not be able to find anything. So this is the worst case. Why we call this worst case? Because this comparison will be executed n times, right? And then what is the best case? If I am asking for the first element of the array, if I am searching for, in this example, k is equal to 1, then that is bingo in the first step, right? So I will just check the first position and I will find it. So with the best case scenario, I will have only one comparison, but with the worst case scenario, I will have n comparisons. So that makes a difference, right? So that is the difference that is based on my input. And there is also another case, which we call the average case scenario. With the average case scenario, actually, I need to have some average input. On the average, what will be the input look like? So usually, if you make the more sophisticated mathematical analysis, with the more sophisticated, I mean, it's not that much sophisticated. So let me tell you a little bit about it. So let's assume P represents the probability that you will find the key on the given array. And if each position has the same chance of having this key, okay, then what will happen? So you will go to the first position with the probability of P over N, you will see that it is there, right? With the probability of P over N, you will see that it's on the second position. With the probability of P over N, you will see that it's on the third position. If it is on the first position, you will need to make only one comparison. If it is on the second one, you will need to make two comparisons. If it is on the third one, you will need to make three comparisons, and this will go on, right? Plus, what can happen is with 1 minus P probability, right? So this will not be on the array. So with 1 minus P probability, you will need to make n comparisons, okay? And if you go to the details of this math, you will see that in such a scenario, if P is equal to 1 over 2, then on the average, you will be visiting approximately n over 2 items in this array. However, as you see, for the best case and the worst case, I was able to tell you the scenarios very easily, but when it comes to the average case scenario, so it becomes a bit more difficult. And that's actually what happens in practice also, okay? But moral of the story, when we are analyzing an algorithm, we should pay attention whether our analysis is a worst case, best case, or average case scenario. And actually, from a computer science perspective, best case scenarios are not very much interesting. They are not useless, but not very much interesting. All CS people are mostly pessimistic. Okay, so pessimistic because we would like to make sure what can happen in the worst case and be well prepared. That is why the worst case scenario is the one that we usually focus on. However, the average case scenario that is very useful when an algorithm becomes something used in practice, okay? Because at that time you will have some real world input and you will have an idea. But with the average case scenario, as we discussed in this very simple example, so you should build a model, and this model will include some probabilistic aspects. So that is a bit more complicated. But we will have some examples later about this average case scenario as well. Okay. So one last thing maybe I should mention. What is the importance of the order of growth? Okay. So when I would like to just show you that what happens to different functions in different n values. Okay, so let's say here, fn is equal to log n. Usually in CS, we do not write this subscript, and whenever we see a log, we assume that it is base 2, okay? In CS, if you do not have a base for a logarithm, so you should assume that it is log 2, okay? So in other fields, if there is no base, you should assume log 10, but this is not the case for us. For instance, log n. Okay, so what happens? So here I have n is equal to 10. So if I take the logarithm of this 10, it will be something like 3.3, okay? When it is squared, okay, so now my input size, let me say, is equal to 100. So what happens to fn function? You see, it becomes 6.6. You see, n is squared. However, fn is just doubled, right? So you keep increasing the size of this n by multiples of 10, but you see these are only incrementing in steps of around 3, right? So that is for fn is equal to log n. So whenever you say fn is equal to n, we observe a linear increase, right? But it is important to observe that. So when the function becomes more than polynomial, so let's say beyond n squared, n cubed, okay, so at this part, these are really very huge numbers, okay, so we call this the exponential. So when n is equal to 10, right, 2 to the power of 10 will give me something 1024, and it's approximately 1000, okay. When you just square this input size, so 2 to the n becomes something really, really, really very huge, okay? So when you compare this one with this one, okay, we see that it is more than 10 to the power of 27 times greater. Only you just make an n from 10 to 100, okay? So that is why exponential and factorial functions, they grow very fast. Log n, not very much, right? So n is a linear growth. N log n is a little bit more than n, but less than n squared, right? When it becomes an n squared and n cubed, so these are the polynomials which we start to feel the pressure, but when it becomes exponential and factorial, it's really huge. This will be more meaningful with the next video when we visit the asymptotic notation. Okay, so in this video, what we did is we just make an introduction to the algorithm efficiency, and these are the important points we should have from this video. time and space efficiency of algorithm is a mathematical function with the algorithm's input size. By the way, how can you measure the input size? Input size is sometimes very trivial. So I'm given an input array of size n. Okay, so that is an integer array, right? However, to be more precise, although we will not need it in this course, but in further courses, it is always very good to think about the input size as the number of bits that are provided to the algorithm. Okay, so if you think about the binary representation of what is being input to this algorithm as the input size, it will be safe. For instance, let's say you would like to compute the greatest common divisor between two numbers. So these are just numbers, right? Just integers. Then how will you decide on the order of growth of such an algorithm? What will happen? Actually, you are curious. You are curious about what will happen if I would like to compute the greatest common divisor between very large numbers. Okay. Then I start with a number of size, let's say n bits long. And what will happen when this becomes n plus 1, n plus 2, 2n, 3n, 4n, 5n bits? So that is why you may be thinking about the input size as the binary representation of this input. However, most of the time you will not need it. Just the array size will give you enough intuition. Okay, what else? So we have time efficiency. To measure the time efficiency of an algorithm, I will just count the number of instructions that will be executed. Since the algorithm is provided as a pseudocode, I can see the line-by-line instructions, and I will assume that all those instructions take equal amount of time. Why? Because I'm assuming a hypothetical RAM machine on which all operations have the same execution time. Okay, so that is why counting the instructions will be n. And we have the space efficiency. Again, that is the extra memory that I will need during the executions, and both of them are functions of the input size n. Okay, and with this theoretical analysis, what we will be providing is what will happen when the input size goes to infinity. So this is the main question we are curious about. And all those theoretical analysis depends on the type of input, okay? The type, I mean, is this a best case scenario? Is this a worst case scenario? Or is it an average case scenario? So while analyzing an algorithm, you might have the best case complexity, the worst case complexity, and the average case complexity separate from each other, both for time and space efficiencies. Okay. Yes. So that concludes our introduction to the algorithm efficiency. On the next video, we will continue with the asymptotic notation. Thank you.